The focus of this presentation is going to be on time effects. Concrete is going to deform over time due to shrinkage, creep, and temperature effects, so we need to be able to account for these in our designs. By the end of this section, I want you to be able to identify the main time effects, describe at least one reason why time effects matter, explain and illustrate the basic shrinkage mechanism, differentiate between external drying and autogenous shrinkage, list the primary factors affecting shrinkage and explain how each affects it, explain the basic mechanisms of carbonation shrinkage, use ACI 209R to estimate shrinkage strain and creep coefficients, explain and illustrate the basic creep mechanism, list the primary factors affecting shrinkage and explain how each affects shrinkage, explain how superposition and the effective modulus method are used to account for time effects, and then finally, use the effective modulus method to calculate stresses and deformations caused by time effects. Concrete will deform over time because of shrinkage, creep, and different temperature effects. You can see here a plot of our strain versus time in our concrete. You can see that the main components are shrinkage, initial strain due to any applied load, and then also creep that occurs because of this applied load that's sustained on the concrete. Concrete time effects are important because they'll impact the long-term behavior of our concrete and the design of our concrete. One example of how our time effects affect our behavior is with our pre-stressed concrete members. Shown here is a plot of our pre-stressing strand stress versus time. We'll initially jack our pre-stressing strands to a certain stress, and this tension in our pre-stressing strands is going to put the bottom of our section in compression, which is what makes our pre-stressing effective. So what happens is over time, this strand stress will become less effective because of concrete time effects. So we'll have some initial loss in our pre-stressing due to anchorage seating losses and relaxation and temperature losses. Then when we transfer the strand stress into our beam, we'll have an initial elastic shortening loss. And then over time, our creep, shrinkage, and relaxation of our strands will cause an additional loss. So the creep, shrinkage, and relaxation, primarily the creep and shrinkage of concrete is what we're going to focus on in this section. The strand stress that we saw in the previous slide is going to impact the bottom fiber stress of our section. So when we first transfer the strand stress to our beam, the bottom fiber of our beam, highlighted here, is going to be in compression. Then over time, as our strand becomes less effective due to creep, shrinkage, and relaxation, our bottom fiber stress is going to go down. When we place a deck on the section, we're going to have another loss of bottom fiber compression. When we place any additional superimposed dead load, we'll have another loss. And then eventually when we place a live load, we want to make sure that the bottom fiber stress doesn't go past cracking in our pre-stress member. So pre-stress losses will affect the stress in our concrete over time. And this is one instance where our concrete time effects will impact our design. So now we're going to take a look at the different concrete time effects, and we'll start with shrinkage. So shrinkage is essentially the decrease in volume of the concrete due to water movement. So we have water moving and required for hydration, and this is called autogenous shrinkage. And then we also have water lost to the environment, which is called environmental or drying shrinkage. And what shrinkage will do, essentially, is we have water that's contained in our pores, in our concrete pores. And when water wants to leave the pores, it's going to cause some kind of pore water pressure in the pore. So this pore water pressure is going to make our concrete want to shrink. And the shrinkage is going to be resisted by the stiffness of our concrete EC. So we can see that our shrinkage is some function of our pore water pressure divided by our stiffness. and that would give us our shrinkage strain. So we can see that our shrinkage is driven by a change in pore water pressure and resisted by the stiffness of the concrete. We can look at shrinkage another way by seeing how our shrinkage develops over time. We can look at our relative humidity versus time, our concrete stiffness versus time, and our total shrinkage versus time plots. So first we can see that our shrinkage is primarily driven by the difference in relative humidity between the internal relative humidity of our concrete and the external relative humidity of our concrete. Essentially, the concrete wants to equilibrate with the external relative humidity or the environment. So this internal relative humidity wants to decrease to the level of the external relative humidity. So this is going to be driving that pore water pressure that we looked at in the previous slide. We also have our concrete stiffness, which is changing over time. So at the beginning, we have the largest difference here. So we're going to have our concrete wanting to shrink the most at the beginning, and we have the least stiffness. So most of our shrinkage is going to happen up front during the first couple months because of this. We have the largest pore water pressure, and we have the least stiffness. As our stiffness increases, our concrete's going to be want to shrink less. There's going to be more resistance to shrinkage, and our this difference between internal relative humidity and external relative humidity is going to decrease. So that means that our shrinkage is going to, or our increase in shrinkage is going to decrease over time. This is highlighted again on this slide, where we can see that early in the concrete life, there's the largest driver for shrinkage and the smallest stiffness of our concrete. So this leads to the largest shrinkage, or the largest amount of our shrinkage occurring early in the concrete's life. As I had said, our drying shrinkage is going to be our main type of shrinkage, and this is caused by loss of water from internal pores in the cement matrix, either to the environment or to cement hydration. For water loss to the environment, this is called environmental drying shrinkage, and water loss to further hydrate the cement, this is called autogenous shrinkage. Our environmental drying shrinkage is going to be affected mainly by the environment and the shape and size of our specimen. So here, if we had a rectangular beam just placed out in the desert and one placed in let's say the Florida Everglades, and we came back a year later, the specimen in the desert would shrink more than the one in the Everglade because we have a drier climate in the desert than the Everglades. If we came back a number of years later, we'd see again the specimen in the desert would have a greater amount of shrinkage than the one in the Everglades. Our autogenous shrinkage is caused by loss of water from the internal pores in the cement matrix to hydrate our cement. So we looked at in the last section how cement is hydrated, and we saw that our C3S and our C2S react with water to form CSH and CH, which are our two main components in our hydrated cement paste. So we have this water here, but where does the water come from? So early on, water comes from it's free water before the final set. But after final set occurs, the additional water comes from the internal pores. And as the water is pulled from these internal pores, we have a pore water pressure that drives our shrinkage. So whether autogenous shrinkage or external shrinkage are more significant depends on the water to cement ratio. Lower water to cement ratios are going to have lower or lead to lower permeability concretes, and they're going to have more cement to hydrate. So this means that our autogenous shrinkage is going to be higher than our external drying shrinkage. It's going to be harder for water to leave the member to the environment, which is going to keep the external drying shrinkage down, and it's going to give more cement that needs hydrated, which is going to increase our autogenous shrinkage. After we get above around a water cement ratio of 0.42, we're going to have external drying shrinkage become the primary factor compared to autogenous shrinkage. And this is because higher water cement ratios are more porous, which means it's easier for water to leave to the environment, and there's less cement to hydrate, or more water to hydrate that little cement. So this will decrease our autogenous drying shrinkage. This is highlighted again on this slide, where we see that lower water to cement ratios result in the majority of the water being required to hydrate the cement. And we're going to have lower permeabilities, which make it harder for the water to leave the environment. Again, we'll see that a high water to cement ratio means that our concrete's more porous, so more water can move to the environment, which means we'll have a higher external drying shrinkage. We'll also have more water left over after hydration to continue to hydrate the cement, which will decrease our autogenous drying shrinkage. Shrinkage is also going to be dependent on the ability of the water to move through the concrete matrix. A high permeability concrete will have capillary pores that can be interconnected within the CSH framework. In this concrete, it's really easy for water to move through the concrete and to the environment. In a low permeability concrete, our capillary pores are not connected or only partially connected in the CSH framework. In this case, it's harder for the water to move throughout the concrete, the pore water to move throughout the concrete and to the environment. So essentially, it's easier for the water to move if our capillary pores are connected. And our capillary pores are connected, or we have high permeability when we have higher water to cement ratios. Our shrinkage is also going to be dependent on the energy required to remove the water from the pores. So our pores are going to be at different scales. We can have small and large gel pores that are between the CSH, and we can also have intraglobal pores that are actually within the CSH itself. So the smaller the pore, the more energy required to remove the water from the pore. So it's going to take more energy to move water from the intraglobal pore than it will from our small and large gel pores. So that means any water movement that is in these smaller pores is going to require more energy and cause a higher pore water stress, which will increase our shrinkage. Now that we're done looking at the mechanism for shrinkage, we can look at the primary factors that will affect shrinkage. Shrinkage will be affected mainly by the cement and aggregate content, the aggregate stiffness, the water content, the type of cement, the curing and storage of the concrete specimen, including the relative humidity of the environment, and then finally the size and the shape of the specimen. We can see that the cement and aggregate content is going to affect our drying shrinkage. Essentially, the aggregate is going to give us a higher stiffness normally, and the cement content is going to impact the amount of autogenous shrinkage. So if we look at some results here where we have shrinkage plotted versus the square root of days exposed to drying, so time, and we have a couple different plots for different volumetric contents of aggregate. So essentially no aggregate to 50% aggregate. And we can see that less aggregate means more shrinkage. We can see the same thing here on the right plot, where we have more aggregate meaning less, generally meaning less cement, and more aggregate meaning less shrinkage. So if we have a smaller content of aggregate and unhydrated cement, we'll have a larger shrinkage. A larger amount of aggregate will decrease our shrinkage. So more cement equals more shrinkage, more aggregate equals less shrinkage, and normally more aggregate means less cement. We can also see that our aggregate stiffness is going to impact our shrinkage. So again, our aggregate's going to give us a higher stiffness, which will decrease our shrinkage. And we can see here with our shrinkage plotted versus time for several different types of aggregate, we can see a stiffer aggregate will result in lower shrinkage. So a stiffer quartz will give us less shrinkage than a soft sandstone. We can next see that our water content is going to affect our shrinkage. If we have more water, it means that our concrete will be more porous. So it's easier for the water to move through our concrete and easier for our water to leave our concrete. So you can see here shrinkage plotted versus water content. We can see that more water means higher shrinkage. Looking again here, we can look at the cement content plotted versus shrinkage strain for several different water to cement ratios. A water to cement ratio of 0.3, so less water, will have less shrinkage than a water to cement ratio of 0.7, which will have more shrinkage here. So more water equals more shrinkage. Our shrinkage is also going to be impacted by the type of cement. The cement takes water to hydrate, and the rate and amount of hydration are dependent on the surface area available to hydrate. So if we have a finer cement, it's going to have more surface area for hydration, and the cement's going to hydrate more fully. This means that we're going to have more autogenous shrinkage when we have finer cements. So finer cements equal more shrinkage. Next, we'll see how our curing and our storage can affect our drying shrinkage. Remember that our shrinkage is mainly caused by water movement. So the desire for water to leave the beam to the environment, or to be used within the beam itself or member itself to hydrate the concrete. So if you apply an external source of water, it's going to discourage the larger water from or the water in the larger pores to leave, which will discourage water in even the smaller pores to remain in the smaller pores. So this means there will be less water movement. It'll also mean that there's more water to hydrate the cement. So better curing is going to provide more water to the concrete during hydration, which will decrease the autogenous shrinkage, and we're going to have a denser concrete or a denser concrete matrix towards the outside where we're curing. So this is going to decrease the permeability, which will decrease our drying shrinkage. So better curing is going to equal less shrinkage. We can also see that the external relative humidity is going to impact our shrinkage. Here we have shrinkage plotted versus time for 100% relative humidity, essentially a specimen in water, 70% and 50% relative humidity. We can see that with the 100% relative humidity specimen, we'll have a little expansion that occurs as the water is absorbed from the environment and used to hydrate the cement. We can see that for 70 and 50%, the lower the external relative humidity, the greater the shrinkage. So our shrinkage depends on how easily the water can move through the system and how much the water wants to leave. So for a lower external relative humidity, the water is going to be, we're going to want to leave the concrete more than in a higher relative humidity. Lower external relative humidity equals more shrinkage. The size and the shape of the specimen are also going to impact our drying shrinkage. We need to look at what's the shortest path for the water to travel to leave the beam. If the path's short, such as this bulb T-beam, it's going to be easier for water to leave, so we're going to have more shrinkage. If it takes longer for the water to leave, then we'll have less shrinkage because it'll be harder for the water to leave. We quantify the size and shape of the specimen typically using the volume to surface area ratio, or V over S. Here we can see a bulb T-beam next to a rectangular beam, and we need to look and see how far does the water need to go to leave the beams. We typically represent the distance required to travel to leave the beam in terms of a volume to surface area ratio. So if we have an equal volume, V1 equal to V2, but our surface area in the left beam is higher, so our S1 is greater than S2. So this would mean that our V over S1 would be less than our V over S2. So we can see that a smaller volume to surface area ratio will result in more shrinkage. Here we can see that idea plotted in some experimental results, where we're plotting our shrinkage versus our volume to surface area ratio for a number of different time intervals. We can see that a smaller volume to surface area ratio will increase our shrinkage. Another type of shrinkage is called carbonation shrinkage, or chemical shrinkage. Essentially here, under the action of water and CO2 in the air, calcium hydroxide in the paste is converted to calcium carbonate and forms in the voids. So essentially, this reaction occurs. We have our CH, our calcium hydroxide, reacting with water and CO2 to form calcium carbonate and more water. So our shrinkage occurs because the paste volume decreases when our CH is drawn out and converted to our calcium carbonate in the pores. We can see that water is required to drive the reaction, and it's a product of the reaction. So here's plotted the shrinkage versus relative humidity for carbonation shrinkage is what we'll focus on. So if we have a low relative humidity, we're not going to have any water to drive the reaction. So we'll have zero carbonation or zero shrinkage due to carbonation. If we have a very high relative humidity, water is not going to be able to diffuse out of the member. So if water can't diffuse, we're not going to be able to have this reaction. So we're going to have zero carbonation shrinkage. You can see that the maximum carbonation shrinkage, the just right relative humidity is around 50% relative humidity. So at this point, we're going to have a maximum carbonate or maximum shrinkage due to carbonation. There are several different methods for modeling shrinkage. We have a couple different models from Besant and the B3 and B4 models. These are mainly used for really sensitive structures where you know a lot about your materials. We also have the model found in AASHTO LRFD, the current design specification used for bridge design. This was based on NCHRP 496 model. And then finally, we have an ACI 209R model. So the ACI method is best for any other cases. This is kind of our everyday procedure, and this is what we'll use in this class. ACI 209 outlines a number of different factors that affect creep and shrinkage that they take into account in their estimation procedures. And we see a lot of the ones that we have talked about. So it's a type of cement, slump, air content, fine aggregate, cement content, curing conditions, external relative humidity, our concrete temperature, ambient relative humidity, volume to surface area ratio, curing conditions, what is the sustained load, compressive stress, and stress to strength ratio. So these are the primary factors that are considered in the following expressions. When we're predicting our shrinkage strain, this is a basic expression, a generally accepted relationship relating our shrinkage at a certain time to our ultimate shrinkage, where our shrinkage will increase over time dependent on these constants F and alpha. And our ultimate shrinkage will vary somewhere between 415 and 1070 microstrain. ACI 209R gives us two different expressions that we can use depending on if we are moist cured or steam cured. So we can use these two expressions. And what you can see is if we're steam cured, we're going to develop our shrinkage a little more slowly, but ultimately both our steam and moist cured are going to end up at similar ultimate shrinkage strains. ACI 209R provides both equations and tables. So you can see here is a table with the same values as would be found using the equation. In order to find our shrinkage strain at different times, we need to find our ultimate shrinkage strain. And we can find our ultimate shrinkage strain using the expression shown here, where we have a gamma sub SH shrinkage that is a combination of a number of different gamma factors taking into account our initial moist curing, our ambient relative humidity, our volume to surface area ratio, and our concrete composition. Next, we'll step through some of these different factors. First, we can look at the initial moist curing length, this gamma CP factor. You can see that if we have a shorter moist cure, we need to increase our shrinkage strain by 20% compared to the 7-day moist cure that's assumed by the expression. If we moist cure for longer, then we can decrease our ultimate shrinkage. So longer moist curing will decrease shrinkage, as we saw before. Next, we have a factor taking into account the external relative humidity. If we have an external relative humidity between 40 and 80%, which is where we'll typically be, we can use this expression. If we have a relative humidity greater than 80, then we have a different expression. And this is also in table form, we have a different factor for creep and shrinkage. So we can see that a higher relative humidity will decrease our shrinkage. The next factor takes into account the volume to surface area ratio, which takes into account the shape of our specimen or beam. So here we have our volume to surface area ratio, and we need to know how to solve for this ratio. So I'm going to show here how we can find it for this rectangular beam, which has a cross-sectional area of 20 by 12 and a length of 240. So the first thing that we can do is find our surface area, taking into account our two ends with area of 20 times 12, our two sides with 240 times 20, and the top and the bottom with a size of 240 times 12. Then we can find the volume, which is just our area, 12 times 20 times our length, 240. And then to find our volume to surface area, we just take our volume divided by our surface area to find our V to S ratio of 3.64 in this case. We can then plug in our 3.64 into this expression for gamma VS to find our gamma factor. And note that we can generally ignore the end faces of the member. The end face will normally have a minimal impact on the volume to surface area ratio. Next, we have 4 factors that take into account the concrete composition. The first factor is our slump factor. We can see a higher slump will generally increase our shrinkage, and this is because higher slumps normally indicate a higher water content. Next, we have a factor taking into account the ratio of fine to total aggregate. The more fine aggregate that we have, or the higher this ratio, the less coarse aggregate. And our coarse aggregate, not our fine aggregate, is what resists shrinkage primarily. So if we have a higher amount of fine aggregate compared to our total aggregate, then we'll generally have more shrinkage. Our next factor takes into account our cement content. If we have more cement, we're going to have larger shrinkage. And the final factor takes into account the air content. Air can't resist shrinkage, so the more air that we have, the more shrinkage we'll have. On the next few slides, we're going to go through an example problem calculating the shrinkage strain using ACI 209R. We're going to find the shrinkage strain at 28, 90, 180, and 365 days after the application of the load, assuming that the following information is known. So we're assuming that we moist cure for 7 days, that the age at loading is 28 days. This isn't important for our shrinkage calculations, but we're going to use the same example for creep, so that's why we need to know the age at loading. Our external relative humidity is 70%. We're considering shrinkage from 7 days after casting. This is after moist curing is done. So the shrinkage should be considered from the point when our moist curing is finished. We know our volume to surface area ratio is 3.5 inches. We have a 2.5 inch slump, 60% fine aggregate, 752 pounds cement per cubic yard, and 7% air content. The last thing is we're also going to find the differential shrinkage strain for the period starting at 28 days after application of the load. So we'll see how to do that on the next slides as well. The first step is to calculate all of our required coefficients. This is essentially just plugging in all the values from the previous slide into our expressions that we went through from ACI 209R. We find our relative humidity factor, our volume to surface area factor, moist curing factor, slump factor, fine aggregate factor, cement content factor, and air content factor. So we're going to use all of these factors to find our ultimate strain on the next slide. The next step is we need to use our coefficients to calculate our ultimate shrinkage. Here what we're doing is taking 780 microstrain times each one of the factors on the previous slide. So all the factors times each other on the previous slide would give us 0.562. So we're taking 0.562 times 780 microstrain to give us an ultimate shrinkage strain of 439 microstrain. We can then also calculate the shrinkage at each time. So what I do here is we find the time factor, so t over 35 plus t, for different times. We're going to use the time after the initial curing as t in these expressions. And then we can just take this time factor times our ultimate shrinkage strain to find our shrinkage at each of these times. So at 56 days, concrete age, 118, 208, and 393 at these different concrete ages. The last thing that we can do is we can find the differential shrinkage strain from our time 28 days after casting, or concrete, or 28 days after our load application, or 56 days of our concrete age. And what we'll do here to find our differential concrete, or our differential shrinkage strain, is take our strain at a certain age minus the shrinkage strain, within the range that we're looking for. So essentially what we're saying is 78 microstrain are going to happen. 78 microstrain shrinkage is going to happen between a concrete age of 56 and a concrete age of 118. We can then plot the shrinkage versus time as shown here. And you can see that most of the shrinkage is going to happen very early in the concrete's life. Generally, we'll have 90% of our shrinkage will occur in the first year or so. Next, we're going to talk about creep. So creep is the increase in strain under a state of constant stress. If we have two members in, let's say, the desert, and we apply a sustained load on them, they're going to decrease over time. And with creep, the applied and sustained stress is going to have a large effect on the amount of creep that happens. So a larger applied stress is going to result in larger creep. Again, creep is the increase in strain under a state of constant stress. Creep is closely related to relaxation, which is the decrease in stress under a constant strain. So if we have a load that's initially applied on the concrete, we're going to have an initial strain that happens. This is just going to be an elastic strain. And as we keep that load sustained on the concrete, we're going to have an additional strain that happens on the concrete sample. When we remove the load, we'll have an instantaneous recovery that happens. So that's this drop here. And that'll be similar to the initial elastic strain that happened. And if there's still no load on the concrete, we'll have what's called creep recovery. So we'll have some of the creep that had occurred when the load was applied will be recovered. But there will still be some kind of residual deformation that happens, or that will remain in the specimen. We're next going to talk about some of the different types of creep and creep mechanisms. I want to first make two distinctions, the first between basic and drying creep, and the second between short-term and long-term creep. So first, between basic and drying creep. Basic creep is creep with no water loss to the environment. If we have some kind of plastic coating around a specimen, or the specimen's indoors, with some paint or something to prevent water movement, then we'll have basic creep. Drying creep, on the other hand, is creep that happens with water loss to the environment. So we have a basic creep, a constant loads applied, and it's going to deform over time. And drying creep, when we allow water movement, we'll see more creep than if we don't. The second distinction is between our short-term and long-term creep. Short-term creep is a result of pore water movement. So essentially, the water within our pores is moving within the beam or specimen itself, or is moving to the environment for drying creep. Our long and short-term creep, most of short-term creep is recoverable. Our long-term creep, on the other hand, we have it's a result of sliding between the CSH particles, where we have breaking of the van der Waals bonds that are between these particles. So our long-term creep, we have sliding and breaking of bonds and formation of new bonds. So it's going to lead to unrecoverable creep. So that'll lead to the residual creep strains that we saw in the previous slides. Here's a model called the Berger model, which represents the creep mechanism well. So if we have a external applied stress, it's going to be resisted by several different mechanisms. We'll have elastic strain. So this elastic strain will be recoverable. And then we'll also have our long-term and our short-term creep that happen. Our short-term creep is going to be part elastic and part can be modeled with a viscous damper. So the damper would model some of the irrecoverable strains that happen during short-term creep, and the spring would model any of the recoverable strains. The long-term creep happens when our CSH links are broken. So we have this viscous damper that represents our unrecoverable creep. So we have our elastic strain is recoverable. Our long-term creep is not recoverable since it involves breaking of the bonds. And our short-term creep is recoverable, but sluggish compared to elastic strain. Next, we're going to look at some of the primary factors affecting creep. We have our stress intensity, that's going to have the biggest impact. The age when our beam or specimen is loaded. Our aggregate content and type. Our concrete strength, our ambient relative humidity, and then finally also our size and shape of the specimen. The first factor that we're going to look at is stress intensity. Creep is most dependent on the magnitude of the sustained stress. Generally, the larger the stress, the larger the creep. We can see here plotted the strain versus time plot for several different stress intensities. 50% of F prime C to up to 100% F prime C. And what we can see is that for 50 through 75% F prime C, our beam is going to creep, but it won't creep to failure. When we're at 80, 85, or 90% F prime C, we can apply and sustain a load and it will creep until it fails. So generally some of the rules for creep, if we're under 40% F prime C, our creep is going to be proportional to our stress. If we're above 40% F prime C, our creep rate will increase faster than our stress. And if we're above 80% F prime C, our structure will creep to failure. So we want to keep our sustained compressive stresses under 40% ideally, and definitely under 80%. And essentially our summary, a larger sustained stress will equal more creep. We can see that creep will also be affected by the age at which the beam or specimen is loaded. So creep will develop later if it's loaded later. Here we have a plot of our creep coefficient plotted against age and plotted against time when it's loaded. So you can see here, the later that it's loaded, the lower the creep strain at this time, 100 days after loading. If we were to look towards time infinity, these creep coefficients would end up being about equal. So generally, the age at loading is not going to affect our final creep, although it will affect the creep at different times. Here we can see that our aggregate is going to also impact our creep. If we have more aggregate or stiffer aggregate, we're going to have stiffer concrete, which is going to reduce our creep. Here we have our creep strain plotted versus time for different aggregates. And what we can see is a softer sandstone is going to have more creep than a stiffer limestone. Essentially, if we have stiffer, coarse aggregate, we're going to have less creep. Our concrete strength is also going to impact our creep. If we have a higher concrete or higher compressive strength when our beam or specimen is loaded, we're going to have smaller creep. So here we can see our creep plotted versus water to cement ratio. So a higher water to cement ratio would mean a lower compressive strength. So a higher water to cement ratio results in larger creep values. And we can see the same thing if we're looking at our total specific creep plotted versus our compressive strength. A higher compressive strength would result in lower creep. Similar to shrinkage, drying creep depends on water's desire to leave the concrete. And so our ambient relative humidity is going to impact our creep. If we have a higher ambient relative humidity, we're going to have less creep. So shown here is creep plotted versus time for specimens stored in 3 different ambient relative humidities. And we can see that if we're storing the specimen in 100% humidity, we have lower creep than if we were storing it in 50 or 70% relative humidity. Unlike shrinkage, when we have a sustained load, we're going to see a decrease in volume or a creep strains. So we'll see even in 100% relative humidity, we'll see an increase in strains due to creep. But essentially, a higher relative humidity is equal to less creep. Because our creep is dependent on water movement, the size and the shape of the specimen is also going to impact creep. So if we have a higher volume to surface area ratio, it's going to be harder for our water to leave our beam or specimen, so we'll have less creep. Next, we're going to look at several different ways that we can predict creep. Generally, when we're predicting creep, we find what's called the creep coefficient. And we'll talk about what the creep coefficient is in a few slides. The 3 different models that we can use, or the 3 of the more popular models, are the Besant B3 and B4 models. Again, we can use these for really sensitive structures where we know a lot about our materials. In the Besant models, they use what's called a compliance function, J, which is just the inverse of the creep coefficient. We can also use our AASHTO LRFD expressions derived from the NCHRP 496 model, or what we'll do in this class, and what you can do for use as your everyday procedure, is our ACI 209R procedure. When predicting creep, we need to know what the creep coefficient is, which is explained on this slide. So when we place a load on a column or a beam or a structure and keep it on the structure, what we'll see is we'll have an initial sustained stress. This initial sustained stress is going to cause an initial elastic deformation or strain, which we can calculate. And our initial elastic deformation and our initial elastic strain, just our sustained stress divided by our modulus. The question is, what is the additional deformation and the additional strain that's caused by our creep? What the creep coefficient does is it allows us to relate our elastic strain to our creep strain. So this creep coefficient, which is nu or phi or c, is a way to relate our elastic strain to our creep strain. Here again in ACI 209, they provide a table with different factors that will impact our creep and our shrinkage, which we looked at already. Similar to shrinkage, our creep is going to vary with time, and we'll have some general expression as shown here that relates our time-dependent creep coefficient nu sub t with our ultimate creep coefficient nu sub u, where our constants are d and psi, and they vary with time here. And here are some typical ranges for our d's, our psi's, and our ultimate creep coefficient. ACI 209R recommends this expression for concrete that's moist cured for 7 days or steam cured for 1 to 3 days. We can see compared to our shrinkage strain, our creep develops more slowly than our shrinkage. So here's our creep coefficient compared to our shrinkage strain. And again, ACI 209R provides both equations and tables for all of these coefficients. So you can see here our time ratio for our creep strain. Our ultimate creep coefficient, nu sub u, is equal to 2.35 times all of our different gamma factors that account for our loading age, our ambient relative humidity, our volume to surface area ratio, and our concrete composition. So the first factor that we're looking at is our loading age factor. We have two different factors that we can use if we're using moist cured or steam cured concrete. And here we're plugging in the time when we're loading our concrete. The next factor we have here is the factor that takes into account the ambient relative humidity. If we have a relative humidity greater than 40%, we can use this expression. And we can see that a higher relative humidity will lead to less creep. Next, we have our volume to surface area ratio factor. And we can find our volume to surface area ratio the same way that we did for shrinkage. What we'll see is a lower volume to surface area ratio will mean a higher creep. Finally, we have three factors that take into account the concrete composition. The first factor accounts for slump, and a higher slump will lead to a larger creep using ACI 209R. Next, we have the same factor that takes into account the ratio of fine to total aggregate. So a higher fines content will lead to higher creep. And finally, our air content. If we have more air, we'll have a higher creep value. On the next couple slides, we'll go through an example problem. This is the same concrete that we looked at for shrinkage. And we want to find the creep coefficient at 28 days, 90, 180, and 360 days after the application of the load. We're going to assume the following information is known again. So again, we have a 7-day moist cured concrete. Our age at loading is 28 days, which is important now for our creep. We have 70% relative humidity, and our shrinkage is going to be considered from 7 days, which isn't important now for creep. Our volume to surface area ratio is 3.5 inches. We have 2.5 inch slump, 60% fine aggregate content, 752 pounds cement per cubic yard, and 7% air. The first step is to calculate all of our required coefficients. This is essentially using the proper equations from ACI 209R and plugging in our loading age, our relative humidity, our volume to surface area ratio, our slump, our fine aggregate, and our air content to find all these factors. Then we need to take all of these factors times each other to find our ultimate creep coefficient. So the second step is to use the coefficients to calculate the ultimate creep coefficient. We'll take 2.35 times all of the factors on the previous page. If we look at all the factors times each other, we'll get 0.582. So our ultimate creep coefficient, nu sub u, is 1.367. We then need to find our time coefficient for our different loading ages that we're interested in. So we're looking at 28 days, 90, 180, and 365 days after the load application. This t here in our time factor is the time after our load application. So that is our 28 days. So 28, would go in here to find this factor. Then we'll take this factor times our creep coefficient to find our creep coefficient at each of these times. Finally, we can plot all of our creep coefficients versus time, as shown here. And this is the solution to our example problem. In this next section, we're going to see how we can apply everything that we just learned to an actual structure. Over time, concrete shrinks and creeps, and these are going to impact the stresses in our concrete and reinforcement, so we need to know how to include our time effects into our design. We'll first look at the superposition method. In general, a structure is going to have a varying stress applied over its lifetime. So we need to be able to handle complex stress histories. These stress histories can be represented by a series of different applied and sustained loads. So this stress history with different steps can be represented by a series of sustained loads, where the first step we have F sub C1, then we need a negative stress to apply and sustain to bring us from C1 down, or FC1 down to this point, which will be FC1 plus FC2. And then we have a small step up, so we'll have a small increase, so a small sustained load here, FC3. So we can keep doing this for any type of additional steps that happen during the life of the structure. Each of these sustained stresses is going to have a strain response. Our sustained load FC1 is going to have an initial elastic strain response and then a creep strain. Same with FC2 and FC3. What we can do then is we can figure out the creep strain at any time as just the summation of these three responses. Next, we're going to talk about the effective modulus method. We'll remember from before what our creep coefficient is. Remember that our creep coefficient relates our elastic strain to our creep strain. What we can do then is we can plug in our elastic strain here in our creep strain and say that our total strain is equal to our elastic strain plus our creep coefficient times our elastic strain. Doing some math then, we can find that our total strain is just equal to our sustained stress divided by our modulus plus our creep coefficient times our sustained stress divided by our modulus, which is just our sustained stress times 1 plus creep coefficient divided by EC. We can see this term we'll call the effective modulus of elasticity, or EC effective. And we'll say that our EC effective is just equal to our EC, our modulus of elasticity for our concrete, divided by 1 plus our creep coefficient. So this is our effective modulus. We can look at our effective modulus another way using the stress strain curve for concrete. Here we have the conventional stress strain curve shown here. And let's say that we apply a certain amount of stress, FCI, and keep it on our concrete. What will happen is we will increase our strain over time. So if we were to put a bunch of different strains on and hold them over the same amount of time, we could get a theoretical softened stress strain response. And this stress strain response would kind of represent our stress strain response under creep, or including our creep effects. And what our EC effective is it's essentially the slope of this softened stress strain response. Before moving on, we're going to do a quick review of our basic principles. First, equilibrium. All analyses must always satisfy equilibrium, which means in our case that our external forces always need to be equal to the summation of our internal forces. Next, we must satisfy the compatibility of deformations. This essentially means that when our different materials are used in a member, the materials are assumed to act as one unit. So our concrete strains are going to be equal to our steel strains. Finally, we have our constitutive relationships, and which are our material stress-strain relationships. For this exercise, we're going to assume linear elastic behavior for our concrete and our steel. I wanted to make a quick note on the interaction between steel and concrete. If we're looking at a typical reinforced concrete column, we'll have both steel and concrete. Over time, the concrete's going to want to shrink and creep. So if we had a column without steel there, it would creep to a certain point. There'd be some kind of unrestrained deformation. Steel is going to resist this deformation, and it's going to create internal stresses. So our column with our steel is only going to deform or strain this much. So we can see that there's a certain amount of strain difference between our unrestrained deformation and our restrained deformation. And this is going to put tensile stress in the concrete and compression in the steel. In the next few slides, we're going to look at how to apply the effective modulus method to an elastic case, to look at creep under applied load, to look at creep under shrinkage-induced loads, and finally creep under pre-stressing force. We're going to have a column with an axial load applied with these concrete and steel properties. The first case that we're going to look at is the elastic case. Here we have a load P0 applied to our column. You can look through the deformation, but essentially we're using equilibrium, compatibility, and our constitutive laws to relate our concrete stress to our force. Here we can see that our concrete stress is just equal to our applied force P0 divided by our transformed area. Note that our modular ratio is our ES divided by our EC. Here's our case for creep under applied load. So again, we have an applied load P0 and we're assuming that it's sustained on our column. Using our equilibrium, compatibility, and constitutive laws, again, we can find an expression relating our stress to our force. And again, we're using our transformed area and modular ratio, but note now our modular ratio is our effective modular ratio, which takes into account our EC effective rather than our EC. And the EC effective is how we account for our creep effects. As I mentioned before, the restraining of the shrinkage caused by the reinforcement is going to cause tensile stress in the concrete. On this slide is the derivation for the expression to calculate the tensile stress caused by this restraint provided by the steel. You can pause the slide pause this presentation if you want to take a closer look, but the things to highlight are we're using again our effective modular ratio with EC effective, which takes into account our creep. And here you can see our force that's driving our stress is our ES times our shrinkage strain times the area of our steel. And note the negative sign denotes that this is causing a tension in our concrete. On this slide is a derivation for an expression to find the concrete stress caused by pre-stressing. So you can again pause the presentation and look at the derivation if you like, but I'll highlight we're using again the effective modular ratio with EC effective to take into account creep. And note that we have a negative sign, so this would be a tensile stress, but generally we're going to have tension in our pre-stressing, so this Fs naught will be negative. So a negative times a negative would give us a positive value, showing that our pre-stressing is going to cause compression in our concrete. Note that we can combine this effective modulus method with our superposition method because all these different components can be made incremental. So essentially we could look at what is the effect of an incremental load or an incremental shrinkage or an incremental pre-stressing, and then just sum all of these components up to find the total effect, similar to the superposition method. Our general procedure for taking into account these combined effects is laid out on the following slides. The first thing that we need to do is we need to compute the time-varying stress due to shrinkage. Because shrinkage happens over time, we need to decide how we want to break up our shrinkage. So we can do it in different steps, or we can lump it all together and apply it at a certain time. But we need to make some kind of assumption and discretize our shrinkage somehow, so that we can take each of these shrinkages and find the stress component caused by them. Next, we want to compute the time-varying stress due to pre-stressing and any initially applied loads at time 0. So any loads that are applied initially, we want to apply, and then see the response, and see how the stress and the effects of creep affect the stress over time. The next step would be to compute the time-varying stress due to other incrementally applied loads. So if we have some kind of other load history, we can represent it by a series of applied loads at different times, like we did in the superposition method, and then find the response to each of these applied loads. Finally, using superposition, we can combine all of these concrete stresses. So we add our initial stress to all of our stresses from shrinkage, to all of the stresses that form later due to additional applied loads. And note that all of these can be at any time during the life of the structure. We can then use equilibrium and our concrete stress to find our steel stress. And we can also find our steel and concrete strains by compatibility. You can now pause this video and go to the complete example problem found in the separate video. In this example problem, we find the deformation at 6 months after casting in the first story center column of this structure below, where we have a lower level cast at a certain time, a first level slab cast at a certain time, then a second level column cast and a second level slab cast at later times. We have our material properties given, and we don't have any information given on our humidity. So again, go to the separate video to see how to solve this example problem. Here's a list of additional references for further study on concrete time effects.